Okay, here we're going to look at a few rates of change problems. And before we begin, last lesson we examined all the rates of change involved in the situation of a fluid, such as water, that is poured at a rate into a container. So the flow of water into container, we've got the change in volume with respect to time, and in most problems that's going to be constant. And as the water fills the container, depending on the shape of the container or the shape of the fluid that is formed, we've got the volume changing as height of the rising fluid changes. Okay, so we've got a dV/dH, rate of change of volume with respect to height. And most likely the subject of the question is determining what is the rate of change of the depth or height of the water level with respect to time. So that's a dH/dt. So we said that, okay, since dV/dt, this is done via the chain rule, dV/dt equals dV/dH times dH/dt. Okay, so it's the multiplication of this rate and this rate can form this rate. Then we can rearrange that to make dH/dt the subject, and it's a division of two rates there. Alright, so let's apply this to a selection of different problems. So a circular slick is increasing at a rate of 5 centimeters squared per second. Now find the rate of increase of the radius of the slick when the area is 400 pi centimeters squared. So first off, we can think about, here is a circular slick that's described here that has a radius, and a liquid is being poured perhaps into the slick, and it's increasing in area, and it's increasing in area of 5 centimeters squared every second. Now we're told we have to find the rate of increase of the radius of the slick when the area is 400 pi. Now the area, we need to relate this area quantity to a circular slick. So area of a circle is pi r squared, and that's what we're going to draw upon. This rate of increase of the radius, we're going to represent that as a dr/dt, so that's that derivative. And we can show that dr/dt is equivalent to this division of rates of change. So first off, what we need to work out is the dA/dH, so how the area changes as the radius changes. So dA/dr is, we differentiate our area rule, and we get 2 pi r. Now we've got the way the area increases over time, so that's that numerator part. So we've put that in, 5 centimeters squared per second, and we divide by 2 pi r. So we're interested now, what is this when the area is 400 pi? So when the area is 400 pi, we can rearrange that for the radius. So area equals pi r squared, and that gives you a radius of the square root of 400, which is 20 centimeters. So when the area is 400 pi, we've got a radius of 20 centimeters. So now we're able to evaluate our rate of change expression. By substituting r is equal to 20, we're going to get this number, 1 on 8 pi centimeters per second. So there's the rate of change. Alright, so that's the general formula for these kinds of problems. Let's have a look at another one. So this particular problem is in fact a VCAR exam problem. This is the kind of problem you might get popping up in an exam 1 of a VCAR Math Methods exam. Oil is leaking at a constant rate to form a circular puddle on the floor, and the oil is being added to the puddle at the rate of 10, there's important information, 10 millimeters squared per minute, causing the puddle to spread out evenly. Okay, so the puddle is spreading out evenly with a constant depth. So it's a puddle, circular puddle with a depth. That's almost like anything that is a circle with a depth is like a cylinder. And when the radius of the puddle is r, the volume is v of the oil puddle, and the volume is given by v equals 2 pi r squared. So it might be worthwhile to show where that comes from. And the job is to find the rate of change of the radius of the puddle when the radius is 30 millimeters. We've got to give our answer with units of millimeters per minute. Okay, so first off, circular puddle on the floor. Alright, so we can illustrate that with a diagram. And it's increasing with a rate. So there's our dV dt, recognizing that's a volume and that's a unit of time. Alright, so there's our first rate. Puddle spreads out evenly and it has a constant depth of 2 millimeters. So we're going to identify d to represent depth, and that's going to equal to 2 millimeters. So there's your circular puddle, and it's in fact like a disc or a very flat cylinder, and it has this height here of 2 millimeters, and that's a constant height. And the volume of a cylinder is pi r squared times the depth. So where the depth is 2 millimeters, we're going to get 2 pi r squared, and that's what we're given here in the formula. So let's go ahead and find the rate of change of the radius. So that is, the radius is an r, and the rate of change is the small part of dt down in your denominator. So we're after dr dt when the radius is 30 millimeters. That's this line of information. We've got to evaluate dr dt when r is 30. Now, dr dt, well, that can be determined as this division of rates here. dv dt divide dv dr. So that's the first bit of information. We know that was given to us at the start here. Now, where do we get dv dr from? Well, we know what volume is in terms of r, so we can differentiate that. We get 4 pi r. So that goes there in the denominator. And the job is to work out what is the value of this rate when the radius is 30. So we're going to substitute r equals 30. And that's 5 over 60 pi, which simplifies down to 1/12, or 1 over 12 pi. And the last part, it says give exact answer with units of millimeters per minute. That's what we've done there. There's the answer in exact form with the units millimeters per minute to get our full marks. Alright, fantastic. One more. So the volume V of water in a dish when the depth is h is given by the rule. There we go. Now this is an exponential function. The depth of the dish is 2.5 centimeters. Now if the water is being poured at 5 centimeters cubed per second, let's find these two parts. So let's break down the information and summarize some of that for us. So the depth of water, which we call h, that's what we've told there, we're going to have h equals 2.5 centimeters. And we've got a rate of liquid being poured into the dish at 5 centimeters cubed per second. So that's a volume with respect to time rate. Now there's the rule of volume in terms of height, in terms of depth. And the job is to find the depth of the water that is increasing. So the depth of water, the rate of the depth is a dH dt. And that's determined by this division of rates, this fraction of rates. Now the numerator is our dV dt, well that's given in the information here, so we can substitute that in. And our rule for volume is given by this. Okay, so from that we can work out dV dH by differentiating. and we get that in simple form, pi times e to the power of 2h. Alright, so part A, let's put that together, substitute that in, and now we're told we have to work out the depth, work out the rate when the depth is 2. So we're going to substitute h equals 2 into the rule, and we get this expression in exact form. And the units for dh dt is centimeters per second. And part B, again, there's the expression, and we're going to substitute this time h equals 2.5. And we get this as our expression. And there we have it. So these are your typical rates of change problems, and please work on the homework for this set, and if you have any questions, please email. Thank you.